Chapter 8. We're going to get back into 3D geometry. We're going to go pretty quick through this chapter. We're going to take a quick look at 3D, as we move from 2D to 3D. In fact, I'll talk about 4 and higher dimensions. We'll introduce a new operator that we have in 3D called the cross product. We'll look at how to represent lines and planes and the triple scalar product as we work with that. And then talk a little bit about how that shows up for lighting and shading in graphics, and then get back to the words you should know. So moving from 2D to 3D is really pretty simple. We already had 2D. We simply add another dimension. In this case, E3. We have E1 and E2 on the plane, and we can go up. We do that by attacking on a third coordinate to every point, adding a new basis direction, E3. And vectors in 3D have 3 components, and as you can sort of guess, in 4D they have 4 components, and in 10D they have 10 components, and so on. Each component indicates a displacement along a particular axis, so a vector in 3D lives in the space of 3 real numbers. In shorter, we just say V is in R3. Points live similarly, okay, and as before, points and vectors in the same space have a similar representation, but points have a position, vectors are actually a direction. We have our standard special vector, the 0 vector in 3D, it's 3 zeros. And we can do lots of other things in 3D. We can talk about the norm, which is a Pythagoras' theorem, or Euclidean norm, which is just the square root of the sum of the squares of all 3 components. In 2D, if you recall, it was just the sum of the squares of the first 2 components. And what do you think happens in 4D? Yep, it's the square root of the sum of the squares of all 4 components, and so on. And this can be interpreted as distance, speed, force, depending on what you're trying to look at. Some very standard operations continue to apply for the Euclidean norm. K times a vector in norm is just the absolute value of K times the norm of the vector. And then, of course, using this property, we can now get to specialized vectors, which are the normalized vector, whose length is 1. If I want to normalize a vector, so here I have the vector 1, 2, 3. I can compute its Euclidean norm, which is the square root of 1 squared plus 2 squared plus 3 squared, which is square root of 14. And then I can make a new vector, W, which is V divided by the norm of V, which is these numbers over here. And we can check that that number is got the norm of 1 by just squaring each of those numbers and adding them up. We can also do things like scale. I can take 2 times V. In fact, here we'll take 2 times V, take its norm. You see it's 2 squared plus 4 squared plus 6 squared, which is 2 times the square root of 14, which is just 2 times the norm we just wanted to see. So in 2D, we talked about the circle of all normalized unit vectors. In 3D, the space of all normalized unit vectors is a sphere of radius 1. So it's sort of similar. We're just now got a sphere of them going on. And that gives us our sort of shape. When we talk about action ellipsoids in 3D, we're going to be dealing with mapping the sphere onto some ellipsoidal shape, which will be in 3D. We have the same thing for the similar product, dot product. In 2D, we had V1 times W1 plus V2 times W3. And in 3D, it's the sum of V1, W1, V2, W2, V3, W3. And you can guess what happens in 4D and 5D, and you'd be correct. Assuming you did V3 or V4, W4, V5, W5. And as before, this actually still gives us the cosine between the 2 vectors. So the cosine of theta is equal to V dot W divided by the norm of V times the norm of W, and that's true in 3D, 4D, 5D, 1000D, whatever we need. But we have something else we can do. So this is sort of gives us the distance, the angle between the 2 lines. But in fact, it's the angle within the plane that contains both of them. As you can imagine in 3D, you have lots of freedom, but if I take 2 vectors, those 2 vectors actually live together in one plane. Any 2 vectors together will live in a plane. And we can start thinking about how to define what that plane is and what's next to it. To get there, we're going to use a new operator called the cross product. So the dot product reveals the angles between them, and the cross product really reveals their orientation and helps define a plane in 3D. So any 2 vectors define a plane, the plane that contains both of them, their 2 lines, unless the 2 vectors are the same, in which case it's not a well-defined plane. The cross product defines a third vector that we can use to complete the 3D coordinate system, and this vector will be orthogonal to U, will be orthogonal to V and W. So we can do this. We can take about the cross product of U equal to v cross w, which gives us a vector v2 w3 minus w2 v3, v3 w1 minus w3 v1, and v1 w2 minus w1 v2. And don't worry if that seems a little hard to remember. I'll show you a trick to remember in just a second. But let's look at some of the important properties of it, and then we'll come back how to compute it. So the first is that u is perpendicular to v and w. That is, u dot v is 0, and u dot w is 0. And you can go back to the definition, just multiply it out, and you'll see why that all happens. Things all cross out. The orientation of u follows what's called the right-hand rule, which I'll see in the sketch in a second. The magnitude of u turns out to be the area of the parallelogram that's defined by v and w. So u is not just a vector in a unit normal sense. It's actually a sized vector, and the size of that vector, the magnitude of it, the norm of it, is the area of the parallelogram defined by v and w. So this gives us a nice way of finding areas for parallelograms. Because the cross product produces a vector, you'll also see it at times called a vector product. It has multiple names depending on what spaces you're working in. V and W, or if V and W are orthogonal and of unit length, then that'll produce a orthonormal U, V, and W. So if U and V are orthogonal, right, so their dot product is 0, and they're of unit length, then the result of the dot product, or the cross product, will be a third vector that is orthonormal, meaning it has unit length and is orthogonal to both of the other two. So I'm going to show you a couple of ways about thinking how to do this. So we already showed you the sort of algebraic formulation of this. One way of thinking about this is that each component is actually computed by doing a 2x2 determinant. For the ith component, you admit the ith component of v and w and negate the middle determinant. So v cross w is the determinant of v2, v3, w2, w3. Take the determinant of that, which remember is this product minus that product. In the middle, we do v1, v3, w1, w3. Take the determinant of that, again, cross, cross, and v1, v2, v3, w1, w2. Okay, now here's another way to remember it. I might still get a little confused with this. First, let's talk about what we mean by the right-hand rule. So here's the right-hand rule shown for two different sets of coordinate systems, just to make it clear. We can talk about the I, J, K coordinate system, where we go from I to J and up to K, or the X, Y, Z, or X, Y, Z coordinate. Okay, I find I, J, K easy to remember because you have your thumb pointing up saying, okay, it's good, right? I, J, K. For X, Y, Z, just remember that the Z is what's pointing up with your thumb. There are times in graphics where they use a different representation. You want to be careful. Remember, this is the right-hand rule. If you have a left-handed coordinate system, this would not apply. It would be backwards. So now, how can we use these to help build something we can remember? So if we just think of the pattern of I, J, K and replicating them, we're going to write down actually a three-dimensional matrix of I, J, K, the ith, jth, kth component of V, ith, jth, k component of W. And now we're going to build this, sort of expand them because they're cyclic. We're going to do IJK, IJ, we'll do IJK again. So we just replicate the data. And now this is an easy way to think about how we're going to do this. We're going to take this direction, so I, V2, B, W3 minus V3, W2. So let's do that in a broader example so we can sort of walk through it. So assume I have two vectors, A and B, which are A1 times I plus A2 times J plus A3 times K. Now, we could draw these as a vector. Here we're using a more EE or physics type notation where we're thinking of I, J, and K as basis vectors. We're going to just write them out that way. So A cross B, the cross of these vectors, turned out to be the determinant of that 3x3 matrix. So this is also going to show you how to do a 3x3 determinant. Which is true even if it's not for a cross product. So what we're going to do is we're going to take that cyclic pattern I wrote out and say we're going to take the first one. We're going to go from I, we're going to go right and get A2, B3. So we're going to have I, A2, B3, and then we're going to subtract off going backwards. So I, A3, B2. And then similarly for J, we'll get the next one. We're going to do A3, B1, and minus A1, B3. That gives us this term. And then for our last term, we do the same thing. We get just go sideways from K. We get A1, B2 minus A2, B1. And that gives us what the cross product is. And here, this is the ith component. So the first element of the vector, the second element of the vector, and the third element of the vector. And as you go to work that out, you can just fill in some numbers. You can see that this works out pretty easily. Because it's sort of visual, I find this technique good to remember. If you can just remember the formulas, good for you. So just to walk through an example, make sure you can do this on your own. Given V of values 1, 0, 2, and W of 0, 3, 4, we do the cross product. We get 0, 4 minus 3, 2. 2, 0, 2 times 0 minus 4 times 1, and so on, gives us this vector. So you should be able to do this given any pair of vectors before we get click questions. So as we said, this gives us the area of a parallelogram. To sort of see how we get this, sort of analogous how we did stuff in 2D. We can think of this by looking at the length of V, the length of W. We get the height here as H. H is equal to the magnitude of W sine theta. The side of the length is equal to V. Okay. The interesting thing about this is it tells us that P is also equal to the magnitude of V, this length, times the magnitude of W, times the sine of the angle in between them. And if we actually equate those two expressions, V cross W equals this, right? We now have a formula that tells us, in terms of the magnitude of the cross product, that it's the length of V, the length of W times sine theta. In fact, it is given by this area. So if we're asked to compute the area of a parallelogram formed by two vectors, we just go ahead and compute the cross product, take its norm, and we get, in this case, 2 square root of 2. And if you want to verify this, because in fact these two things form a nice rectangle, it's just the area is the product of the lengths, because the sine of 90 goes away, so it's just 2 times the square root of 2. So I draw this one out. Make sure you can walk through doing a computational product given two vectors. Now it turns out we can reuse some other stuff to relate this down to the dot product. So if I start with this relationship on the magnitude of the cross product, and I square both sides, if you just square the right-hand side, I'm going to get V squared magnitude, W's magnitude squared, sine squared. Now we're going to use a trig identity that sine squared is equal to 1 minus cosine squared. Now we see that that's a product. We can multiply that out, so we get the 1 and the cosine squared. And now we're going to use the fact that we already know that V dot W is equal to the magnitude of V times the magnitude of W times cosine. And so V dot W squared gives us the second term. And this gives us a way of relating the cross product's magnitude to the magnitude of the vectors and the dot product. And so this is an expression for the area of a parallelogram in terms of the dot product as well. So coming back, reviewing the properties of a cross product, the parallel vectors result in a 0 vector, so V cross any constant times V will be 0. It's homogeneous, so if we multiply by a constant, it just gets pulled out. C times V cross W is equal to C times V cross W. And C times W would cause the same thing. It has a property what's called antisymmetric, so we talked about symmetric properties where for the dot product, V dot W is equal to W dot V. Well, for the cross product, it's antisymmetric. V cross W is equal to minus W cross V. In fact, you can sort of see that if you think about the way the right-hand rule works and the directions you have to point if you change the order and you want to go in the other order. So when we do the right-hand rule, it's W is the first element, V is the first element, like the ith component or the x component, W, right? We do a cross product. You go in the other opposite direction, you got to flip it over. In general, it does not commute. So if I have V cross or U cross V, the association, the quantity V cross W, it's not equal to U cross V's quantity times the cross with W in general. There are cases for which it's true, but in general it's not. It does distribute, however, so I can do U cross V plus W, and I'll get U cross V and U cross W plus. So the right-hand rule, if we actually want to think about it, we can think of the three basis vectors, E1, E2, E3, or IJK, or XYZ, whatever you want to think of them as, and take any two of them and cross it, you'll get the third one. In terms of orthogonality, we get the property that V dotted with V cross W is 0, so that V cross W is orthogonal to V, and similarly is orthogonal to W. Okay? So those are all the properties. Just to sort of walk through a couple of them as numbers, just sort of test them out. So we're going to do some tests with just the three vectors U equals 1, 1, 1, V equals 2, 0, 0, and W equals 0, 3, 0. So first, just to see that if I take V and 3V and take their cross product, again, I'm not going to go through all the steps, but you can sort of verify this. If you're not comfortable with the cross product, I actually strongly recommend you take some of these numbers, use these as your practice test to go through and compute the cross product, so you can sort of see we get 0, 0, 0, 0, and then we get 0, 6, right? 3 times 2, this one, and 0 times 0. So we get the 2's and 6's here. They still don't cancel out, and 2 times 0 and minus 6 times 0 for the last component. So all of that works out to 0. To see that it's homogeneous, again, just going to walk through, put these in, and walk through, multiply out all the cross products. So it's a good way to practice a couple of cross product things. To see it's antisymmetric, if I take V cross W, that gives me the vector 0, 0, 6. But if I take minus W cross V, you'll get minus 0, 0, minus 6. Non-associativity, in this case, if you just work out a couple examples with these three, you'll find out it's not associative. So in this case, V cross the quantity, U cross the quantity V cross W gives us this vector of 6, minus 6, and 0. And the quantity U cross V crossed with the quantity W gives us 6, 0, 0. Similarly for distribution, you can just put these in. So multiply them out. First, here we get two different cross products, add them together. Here we add the two vectors, V and W, and then do the cross product. So we'll get 1, 1, 1 crossed with 2, 3, 0, giving us minus 3, 2, 1. So that's a bunch of properties of the cross product. You should know them, be able to use them, be able to compute them pretty easily. So now we're going to move on to geometry in 3D. So we're going to talk about lines. So if we want to specify a line in 3D, it's a little bit different from 2D. So we can't just take 2 points or the explicit representation of a line. In 2D, right, we had a point plus a vector perpendicular to the line. That technique, which we didn't spend much time on, doesn't work because I didn't spend time on it because it doesn't generalize. But we can think of an entire family of lines that satisfy a family of lines, because any line that is perpendicular, anything that's perpendicular to a line will actually give us a plane. So in 3D, we're going to use the concept of a normal to a 3D line. You can ask about it, but it doesn't really exist, right? For any line, any plane is perpendicular to that line in some direction. So that doesn't help us. So because of that, there turns out to be no implicit 3D form for a line. Okay, but we do get our parametric representation. So we can take a point plus t times a vector, where now the point is in 3D and the vector is in 3D, which is really the same as we did in 2D, except it's in 3D. And as you can guess, the parametric form exists for 4D, 5D, and as many Ds as you need to. But there is one other thing that's important to remember as we go to higher dimensions. In 2D, a pair of lines either intersect or they're parallel. Those are really the only two choices. Either the two lines never intersect and they're parallel to each other, or they will intersect at one point. In 3D, there's a third possibility. The lines are what we call skew lines. If I think about the lines that attached to the face of a cube, the upper left edge and the closer right edge are lines that are not parallel, right? They're clearly not parallel, but because they're on opposite parts of the cube, they never intersect. If I took those two edges on the same face of the cube, then they'd intersect at the corner of the cube. But because they're separated in 3D space, they don't touch. In fact, this other face of the cube has the same possibility. So in 3D, 4D, 5D, 6D, or whatever, lines don't have to intersect. They can be intersecting lines, they can be parallel lines, or in most cases, the lines will simply go near each other, or not very near each other, but they won't actually intersect. If we want to find out if the two lines intersect, of course, we could try writing the representation of a line. P plus t times v, q plus s times w, just this two just general lines. If we go to solve for the value of t and s that solve this, you'll see we get t times v plus s times w equals p minus q. But remember, v, w, p, and q are now 3D vectors, or 3D elements. So we have three equations and two unknowns. And hopefully you remember from high school that that's not always a good position to be. We have three equations and two unknowns. It's what's called an overdetermined system. And very often, no solution will exist that will satisfy all of those at the same time. Now, we can't talk about a technique that will give us the best approximation or the point of where the lines come closest together. That's the topic of chapter 12, and we'll talk about that later. Okay. We still do have the concepts of perpendicular and parallel lines in 3D, but they're just much less common. Okay. So now the next thing we need to talk about is planes. Okay. So planes are a flat area in 3D. And we're going to represent them in what's called point normal form. So here we had point plus vector for a line. For a plane, we're going to have point normal form. And so we're going to define the locus of all points that satisfy the normal dot x minus p equals 0. So n is the normal, so it is a vector. P is a point. It's a point on the plane. And then we're going to look at all points such that when I subtract x from p, that's a vector in the plane. X minus p is a vector, and I take that dotted with n is normal. That means it's perpendicular. So that is why it defines a plane. All the points x minus p live in the plane such that when you dot them with n, they're going to be perpendicular. If the length of n is equal to 1, it's called the normal to the plane, or the unit normal to the plane. Okay. Now to see what this means algebraically, let's go take that dot product and just expand it out. We're going to take x minus p and dot it with n. So we get n1 times x1 plus n2 times x2 plus n3 times x3. That's just the first part of the dot product. Remember, they associate and distribute. So we can then take minus n1 p1 plus n2 p2 plus n3 p3. Right? We've just collected together all the terms. Now if I look at that, I can actually see that that's of the form ax1 plus bx2 plus cx3 plus d equals 0, where a is equal to n1, b is equal to n2, c is equal to n3, and d is equal to minus n1 p1 plus n2 p2 plus n3 p3. So this is an equation that looks like, in what you might have seen in high school, ax plus by plus cz plus d equals 0, or ax plus by plus cz equals d. All of those are different ways of just rewriting with slightly different constants that come out of it. So if I want to find the implicit point of a plane that goes to the point 4, 0, 0 that is perpendicular to vector 1, 1, 1, basically you can compute minus d by just looking at the point, right? Minus n1, 0, and 0. So I get 1 times 4 plus 1 times 0 plus 1 times 0, right? I'm just taking that normal and the point. That gives me d is minus 4, and then I can just read off the coefficients of a, b, and c. So I get x1, 1x1 plus 1x2 plus 1x3 minus 4 equals 0. That gives me the equation of the plane. You can sort of see why this could be pretty easy to compute, because if I have the point and the normal, it's easy to get the constant and it's easy to get the coefficients of the plane. So now let's look at this a little bit geometrically. If I want to think about how far is the plane from the origin, it turns out that that constant d gives us that distance. So even though there's some point on the plane p that we used, the distance from the origin, okay, is the perpendicular distance, and we can see that that's equal to cosine of theta divided by d times the norm of p, cosine of theta divided by d, this distance here, times the hypotenuse, right? Sakatoa, so right, we got cosine is equal to adjacent divided by the hypotenuse. But we know that we can also get d as n dot p, and we can get the norm of p, assuming that it's a unit normal. We can just put the norms on the bottom, and that gives us that d is equal to n dot p. Right? So we're just relating these two as another way of getting that. So if I have a more general question and I want to get a distance of some other point x to the plane, its distance is d, where d is equal to just put the point into the implicit equation, ax plus ax1, bx2, cx2 equals d. We can convert this plane to point normal form. Okay, normalize by n, divide the implicit equation, and we'll see that for this, a prime is equal to a divided by the length of n, b prime is equal to b divided by the length of n, c prime is c divided by the length of n, d is d divided by the length of n. So again, if we have a unit normal, all of this is just going to give us that our equations are the right distances. And you can see for any point d, x, this gives us the distance of a point to a plane. Now, from a graphics point of view, that can be pretty interesting, because now if I have some plane and I want to say how far away am I can just take the implicit form of it and compute the distances. Okay, so given, for example, assume I have a plane x1, x2, x3 minus 4. This plane is not in point normal form because n is 1, 1, 1. The length of n is actually 1 over the square root of 3. So if I want to put this in proper point normal form, I want to normalize it. So I'm just going to divide everything by 1 over the square root of 3, which gives me this equation for the plane in point normal form. And then if I have some other point, say q equals 4, 4, 4, from the plane, all I have to do, given that it's normalized, is put that in, and I'll get this about 4.6. So that tells us two things. First, its sign, the fact that it's positive, it lies on the same side of the plane as the normal, and 4.6 gives us the unit, the sort of length or distance away it's going to be. So it tells us both the side of the line it's on and the distance to the line, because distance is signed. Okay, so how am I going to write a parametric representation of a plane? There's time when I want to draw it, so parametric representation can be useful. So I can do this given 3 points or a point and 2 vectors. And in fact, from 3 points, I'm going to compute a point and 2 vectors. So if I start with 3 points, P, Q, and R, then I'm going to form the 2 vectors, W and V. And for V, I'm going to take Q minus P, and for W, I'm going to take R minus P, and it doesn't really matter. I'm just choosing P as my base point here. And that's going to give us a representation where we're going to say our point plus 2 vectors is P plus S times V plus T times W. And if we want to put that in full barycentric coordinates, we can say that that's 1 minus S minus T times P plus S times Q plus T times R. Right? We're just sort of multiplying all this out, putting them back all in the same thing. So the strength of this is it allows me to create points in a plane. So if I want to walk along a plane by just iterating in it, this is easy. Much like we had for the Bremenham's line drawing algorithm, if I want to draw a plane, there's actually better techniques than just trying to step along it inside of it. If we think about what a plane does, there's another important property which I already mentioned briefly. If I think about a vector, so if I have a point in a vector, the reason I can't use that to define the normal to that to define a line is with one point in a vector, any direction, any plane that contains a vector v goes through that. So there's not enough information to uniquely fit that plane. A lot of data goes through it, which is why we use the idea of a point and a normal to the plane, because then other than the fact that I can have a normal pointing up or down, there's no ambiguity. So point normal form gives the plane a direction, but other than that, there's a unique representation. Here, with a pointed vector, all these lines go through it. No, sorry, all these planes go through this line, this vector. There's some properties we can use. We talked about barycentric coordinates before, and in fact, with the middle point being sort of useful. Well, it turns out that if I have 2 points, there is a way of getting a plane out of those 2 points, or a family of planes out of it. If I take 2 points, I can define the bisector of those 2 points as the plane that is halfway between them in barycentric coordinates. So if I take the point P minus point Q, I can take 1/2 P plus Q, and I can take the normal in such a way that it's equal to P minus Q as my vector. So that gives me a line that's at the midpoint and with an explicit representation of the normal. And with this, it's very easy to get the implicit form, the point normal form of a plane. One last set of properties to talk about in terms of, so we talked about area before. Now I want to come back. Now we've seen planes. We want to talk a little bit about what is the volume in 3D of a parallel pipette. So if I think of a cube, right, I can talk about the volume of a cube, the area of a square, but the volume of a cube. We have the area of a parallelogram and the volume of a parallel pipette. So the area of a parallelogram can be formed, as we saw before, by just taking the cross product of V and W. The volume of this product is really just the face area. If we think of this geometry, I have U and V, that's our base. And now all we want to know is how much is this area of this side, which is just U, length of U, times cosine of theta, because again, we can sort of skew this back over and see it didn't change the area. And since I can view that cosine, I can actually substitute the dot product for the cosine, and we get that the volume is what's called the triple scalar product, or U dot V cross W. And it's actually a signed volume because it's the volume in the right-hand rule. Negative volume would imply that it's in the opposite sign. So given this, the sign volume, the sign and orientation by the three vectors tell us something. If cosine theta is greater than 0, it's a positive volume. U is on the same side in terms of the right-hand rule as V cross W. If it's less than 0, V is on the opposite side of V cross W. And if the volume is exactly equal to 0, then U lies in the plane, and the vectors U, V, and W are called coplanar. So it has 0 volume because it actually lives in a plane. It's just a 2D object in 3D. Turns out that the triple scalar product is invariant under cyclic permutations, which actually, if you want to think about it this way, right, I could relabel these three axes, U, V, and W, in any way I want, and I shouldn't change the volume. So if I take U dot V cross W, or W dot U cross V, or V dot W cross U, that's all perfectly fine. Notice I can't make all possible permutations because if I change the order, if I change U and V and leave W, well then U cross V would be pointing downward, and then I would change it to be negative. So not all 6 permutations, but what we call cyclic permutations, where I just sort of take one, take W off the end, put it in the front, take V off the end of this, put it in the front. Those are our cyclic permutations. This idea of a scalar triple product is really just a fancy name for the 3×3 determinant. We already saw when we went to compute the cross product where sort of how it's related to the determinant. We'll get into that in the next chapter and see it in a little bit more detail. So volume will also be from our 3×3 determinant. Just to make one of those numeric as an example, if we want to compute the volume for our parallel pipette defined by these 3 vectors, first we compute V cross W, giving us 0, 0, 2. Then the volume, we just dot product that vector with U, and we get 6. Notice that if U3 is equal to -3, then the volume is equal to -6. We just change one of these. Sign reversal tells us a lot about the orientation, sort of where they're going to go. Given that this parallel pipette is simply the box, right, of height 2, of 2, 1, and then up 3 in this direction that's been sheared, right? So it goes to 3 through 3. And shearing preserves volumes. The volume is just going to be 2 times 3 times 1, right? Because here we did is just took that third dimension and sheared it to the side. So in 3D we're going to have shearing as well, and that's going to give us a volume preserving operation, and we get volume 6. Okay, so now let's come to the last thing we're going to do in 3D geometry for this chapter. We're going to talk a little bit about what we do when we talk about lighting and shading. So when I want to draw an object and I want to make it shaded in terms of brightness, when you look at this drawing, you probably imagine in your head there's a light source up and to the right of this on this slide, because these facets that are pointing up and to the right are bright, and the facets that are pointing away from it are dark. Okay, and we use this in the concept of shading as a way to decide how much brightness to draw at an object. The normal to a fainter placid goes into this lighting equation. So we have to know what's the normal and where's the light source. And in fact, then we take the dot product. For the simplest part of this, the brightness goes down as cosine. So we just take the dot product between the normal and the light source direction. Okay, and that gives us one part of it. And we also have to know our eye location, because the farther away it's tilted, that'll also be affected. All of those go together in terms of the shading. Okay, so for what's called flat shading, the normal to each of the facets is used to calculate the color. So if I think of a triangle, and this is one of the reasons we use triangles so much in graphics, defined by the points P, Q, and R, I can form the vector from v and w by just taking the normal, right, as v cross w divided by the length of v cross w, so I've got a unit length. Okay, and this gives me consistent orientations of all the vectors. If v cross w is pointing outward, w cross v would be pointing inward, and that gives us sort of our directions. Now, if I want to do smooth shading, I actually want to decide where the light source is. I'm going to take the normal of each vertex to calculate the illumination. And so this gives us an idea. Here you can see the individual triangles in this simple cornet. Or I guess it's just a trumpet, no vowels. And if as you zoom farther out, you're going to get it smoothly shaded. And we do that by taking each vertex and we calculate a lighting vector. That is the angle between it and the light source. And if we want to do some color, we'd be doing this with red, green, and blue components of the lights. And at each point, we're going to compute then a brightness that would go along with this in terms of their surface normals, and we're going to use barycentric coordinates to compute for smooth shading every point in the middle. So we're just going to take a linear combination, S and T, for all the brightness to go in the middle. So for normals, we look at the vertex normals, and we can decide if each of the vertex, each point on that grid has a normal, right? It's a plane. Then for the normals, we can just take the average of the triangles around there to define what's the direction of that vertex. And then given that direction relative to our eye position, we can eliminate faces that are facing away from us. So, right, so here we're showing all these, but there actually are triangles on the backside. We don't want to draw the triangles on the backside, and they're easy to determine because this process of what's called culling, all we really have to do is look at the center of the triangle in the eye's position, and then we're going to look at v by just subtracting the eye from the centroid divided by and normalizing it, and then decide if n dot v is less than 0, the triangle is pointing away from us. If n dot v is greater than 0, the triangle is facing us, and if it's back facing, then we cull it, we get rid of it and don't display it. So not only do we get brightness in terms of shading out of the surface normals, they also tell us when the thing can't be seen at all because it's pointing the other way. Okay, that was a quick introduction to 3D, giving you all the stuff you need to know. A bunch of terminology for those of you who did not do so well with terminology in the closed book part of midterm. Although I'm not giving you extra credit for this, I strongly recommend you write down for each of these words, write out by hand, here is the definition of what those things are.